So we'll move on to question 2 now. And question 2 says the circuits in figure 2 are the same as in figure 1, except that the source or one of the sources has been changed from a fixed value to a variable one. Find the value of the variable source at which the diode changes from conducting to non-conducting, from a conducting to a non-conducting state. So we'll do question 2 part A. And it's a voltage source of V volts, one kilo ohm resistor in series, and in series again a diode. And we have the answers to all of these because it's not a question of whether it's conducting or not. So we now have to make some decision as to what we want to see here. And what we want is a value for V. So we won't say, oh, is it conducting, is it not conducting? We know exactly what's happening here. We know that this will change state when there's 0.7 volts across it, with the anode bigger in potential than the cathode, and there is no current flowing through it. So we know those two things already. So we know that this current here must be 0 amps, and we know that the voltage that lives here across the diode with the anode more positive than the cathode must be 0.7 volts. So actually for this circuit with one loop, this is fairly trivial solution. If there is no current here, there must be no current here, or there, or there, or there, or there, or there. There can be no current anywhere in this loop because there's only one loop involved. If there is no current flowing in this loop, that means there must be no current in the resistor. If there's no current in the resistor, it can't have any voltage across it, because if you were to apply Ohm's law to the resistor, you'd say, well, V is I times R, where I is 0, so it doesn't matter how big R is, V must be 0 as well. So we know that that must be 0 volts, and if we've got 0.7 here, nothing there, that means that this voltage source and this diode are essentially in parallel with each other, or in terms of voltages they are at least. So what we really need to know is, what do I have to do to V to make 0.7 volts with the arrow the other way round? Well, the arrow the other way round is electronics speak for minus. So we know that V must be minus 0.7 volts. And if you don't fancy that, you can say, well, I've got to have that. Change the arrow direction and you get rid of the minus sign. But in general, we would say that this plate of this source is the positive plate. So, and we would usually put the positive plate where the arrow is. So there's a bit of a discrepancy here. You can say that this plate is 0.7 volts bigger than this plate, that's fine. But if you say, what's the voltage on the source? The answer is not 0.7, it's arrow this way up and minus sign there, minus 0.7. And that is the voltage on the voltage source of V volts, which is required to produce 0.7 volts across the diode and no current in it. And that situation is the point at which it switches from being, or changes from the non-conducting to conducting state. The next one is a bit more complicated. We've got two voltage sources now and a resistor and diode. So we've got a voltage source here of V volts that we don't know about, and we've got a resistor in series, which is 3.9 kiloohms, and we've got a diode in series with that, and then we've got a source that we do know about, 6 volts, just in parallel with everything else. Alrighty, well, the same technique applies. We know whatever happens, the current here must be 0 amps, and we know that the voltage across here, across the diode, must be 0.7 volts. So we can say something about the resistor immediately because we can apply Ohm's law, and there's still only one loop. So there's a current that's flowing through all these parts, all these components, and it must be 0 amps through all of them. So if there is no current through this, if there is no current through this resistor, there can't be any voltage across it. So if we say, well, in that case I've got 6 volts here, so this node here is at 6 volts, and then I've got minus 0.7 to here because they're subtracting this from the 6, because the 6 is like that. So I'll take that 0.7 away from the 6 to give me a voltage here of 5.3 volts. Well, because there is no voltage dropped across this resistor, I must have 5.3 volts just there. And if that's the case, well, I'm calling all this stuff here my reference. This is what whenever I write these voltages out, I'm writing them out with respect to ground, or the reference, unless there's a little arrow that says across this resistor across this diode 0.7 volts, across this resistor 0 volts. So 5.3 with respect to ground, well, ground's here, so if I put my arrow like this, that is that 5.3, because it's 5.3 on this node here with respect to this node, this reference node here. So I want 5.3 volts, and it just so happens that because this is the more positive plate of my source, more positive side of my source, that this arrow is in the right place, and V must be 5.3 volts in order to put this diode on the edge of conduction. And C says we've got an unknown voltage source of V volts and resistor in series, which is 3.3 kiloohms, and then we've got, in parallel with those two things, another resistor of 1 kiloohm, and in parallel with the 1k resistor we've got a diode. And we want to know what we have to do to this source to make this diode on the point of conduction. Well, we know that on the point of conduction means 0.7 volts anode to cathode, and no current through the diode. Well, okay, so this bit here is just a potential divider. If I said, well, I'm not going to worry about the diode, because if there's no current in the diode, you don't have to worry too much about what's going on here. The only thing you've got to make sure of is that because the diode and this resistor are in parallel with each other, you're going to have to make sure it's 0.7 volts across the resistor as well. That must be the case because this bit's connected here and this bit's connected here. So what I'm looking for is a voltage which, when out, between 3.3 kiloohms and 1 kiloohms leaves 0.7 volts across the 1 kiloohm resistor. So this is a problem for, really it's a potential divider problem. And you can redraw it if you want to, like this. What does V have to be? Well, overall I've got 4.3 kiloohms. So I should say I'm going to have, alright, we'll do it a bit slower than that actually. We'll work out the current that has to be flowing in this pathway. Now that pathway is this pathway here. So what I'm doing is I'm saying there is some current in this loop here, which I don't know about yet, but it will be whatever current's in this 1K resistor. And there is another loop which goes like this. But this loop has no current in it because there's no current in the diode, so that must be 0 amps. But this loop here, we can figure out what current we have there, and we can say, well, I'll do Ohm's law on the resistor, and that's the same thing as in this circuit, but I'm going to carry on over here because I don't really think this simplification is entirely necessary. It just illustrates what we're doing. So we'll say, well, I want to know what the current is, so we'll say I is V over R, which is 0.7 over 1 kiloohm, and that's 0.7 milliamps. So if I've got 0.7 milliamps there, well, I've worked out what the current is in this loop here now. I know it's 0.7 I know it's 0.7 milliamps. In which case I can say, well, that's the same current that's in the 3.3K resistor. So I can work out how much voltage is dropped across it. I can say, well, V is I times R, which is 0.7 milliamps times 3.3 kiloohms, which is 0.7 times 3.3, 2.31 volts. Yeah, 2.31 volts. So that's 2.31. And then I can say, well, I'm going to apply Kirchhoff's law for voltages around a loop to the loop which involves V, R and R. What I'm really saying is that whatever voltage I've got across here, across the source, must add up to whatever this is plus whatever that is. So I'm going to say that, I'm going to go over here now, well, I'll go up here actually. Our mystery V is equal to 2.31 plus 0.7, which is 3.01 volts. So this must add up to that plus that. This has to be 0.7 because the diode's in parallel with it. This has to be 0 amps because the diode is on the point of conduction, and if that's the case, 0.7 volts there, we can know the current in this loop, 0.7 milliamps, and if we know that current, we can work out what the voltage dropped across this resistor is, and once we've got that, we can say, well, that and that has to add up to that, and that gives us our value for V. Well, the next one is D. We'll do them all, I think. and D is a current source in parallel with the resistor in parallel with the diode. And we don't know what this current is. We know the diode is 1.5 kiloohms. Sorry. We know the resistor is 1.5 kiloohms, and we've got a diode here. Okay. And we can carry on with our usual method of saying if this diode is on the point of conduction, there has to be 0.7 volts across it, and there has to be no current through it. So if that's the case, well, that means because this and this are in parallel, the resistor and the diode are in parallel, there must be 0.7 volts across the resistor as well. Well, now we've got a bit of a problem because the current that flows out of this source should be going that way, and that means that it needs to go down there, and it wants to have a go at going that way and through our diode, but we know that our diode it doesn't have any current flowing in it. But even if it did have some current flowing in it, if the diode was forward biased, we'd like it to be current down the page. So we may find that I turns out to be negative in the end. So we can say, well look, I've got, never mind the current direction at the moment, let's just go with what we know, which is 0.7 volts across that resistor. So I'm going to work out how much current through it, and I know that to call that current positive, I'm going to have to make it in that direction because this resistor has to dissipate some power. And that means the voltage and current have to face each other. So we'll say that I is V upon R. There really is only Ohm's law involved in this, and Kirchhoff as well. If you can get those two down, you can do all these problems, no trouble at all. 0.7 volts across 1.5 kiloohms is 466 microamps. Or 466.66 reoccurring forever microamps. So, okay, well, for this to be the case, we know this current must be doing that, so we have to get rid of that for a bit. Or we don't actually have to get rid of it, but what we need to realise here is that the current which is leaving this source, as the arrow is drawn, is negative, because the current that we have in our resistor, which is making the diode, or rather, the diode is on the point of conduction. So we have to work this way. And what we found out is that there must be some current in the diode, and it's 466 microamps, and it has to be flowing down the page. So what we must say then is, well, that there's a loop here, like this. And the direction of the current in the loop is round and round and round like that. So I is equal to the current in the resistor. There's no option there because there's nowhere else for this current to go except through the resistor. Can't have any current in the diode, remember, because it's on the point of conduction. So I must be minus whatever the current is in the resistor because the arrows face each other. So one of the arrows is the wrong way around essentially. We know what direction this arrow ought to be, so we know this one's the wrong way around. So we can say that, write it in blue to show that it's this I is minus 466.66 reoccurring microamps. So here's our question with the two current sources. Which direction is it going? Upwards. So this one was 9 milliamps, and then we had a resistor which was 2.2k, and then we had another diode and a resistor and another current source, and this one was up as well, and that was 2 milliamps. That's milli. And this was 12 kiloohms. And we used to do our usual thing of replacing the diode with a battery. Now, up to this point, I've just been drawing 0.7 volts on and saying there's no current. If you want to, there is no reason why you couldn't say, oh, I'm going to get rid of the diode. Diode's not switched off. We know okay, it is switched off, but it's on the point of conduction, which is a very special state of switched off. You can say, I've got a battery here, if you want to, which has got 0.7 volts on it. That's fine. And you can say, the current, well, I'd probably draw it that way, because that's the way the current should leave the battery. That should be 0 ohms. In practice, if it's a diode, the current will be going the other way, because, well, there won't be any current, but when I think about it in my mind, I will think about the current going the other way. It's entirely up to you. The algebra will sort out what about the current for you, or in this case there is no current anyway, so it won't enter into your algebra. But I'm going to carry on doing it the way I've been doing it so far, which is just to leave the diode in there and say it's got 0.7 volts across it and it has no current through it. Now, no current there makes this problem relatively, well, it makes it easier than it would otherwise be, because the no current scenario means that there is no method, or there's no means for current in this bit to make its way over to this bit, and there's no means for current over here to get to over here, because there can't be any current in this one, in this branch. So that means we shouldn't expect any current in that branch either. So we'll carry on as before, and we'll say, well, actually, this must be wrong. Yes, that isn't 2 milliamps. That's the prior, not the prior. That's how it was from question 1. In this question, we don't know what the current is. We have to figure it out. So we can pretty quickly work out what the voltage is across this resistor, because we know how much current's flowing through it, because we can sum up the currents on this node here, entering the node. We know that that's 0, we know that that's some current leaving, and we know there's some current coming in here, and that's 9 milliamps. Well, if that's 0 and that's 9, all of this 9 must be headed down there, in which case the current in the 2.2k resistor is 9 milliamps, and we can say, well, V is I times R, which is 9 milliamps times 2.2 kiloohms, and I think it was 19.4, wasn't it, from last time? Because this is the same as before, pretty much. And 9e minus 3 times 2.2 e plus 3, 19.8. 19.8 volts. Okay, so 19.8 just there, which means that all of this stuff here all of that is at 19.8 volts. That's a V of volts. Well, in that case, we know that we've got 19.8 here, plus 0.7 to get us to over here. Well, that's 20.5 over here. So now our question becomes, what current do I have to put through this 12k resistor? Well, that's what the current's going to get up to. What current do I have to put through the 12k resistor to manufacture, or to make it have across it 20.5 volts? And the reason we can do that is we can sum up the currents on this node as we did for this node, and we can say, well, there's no current there, so whatever current comes in here must be going down there. So this will be I amps and that will be I amps, and there's nothing going through the diode. Well, in that case, we can apply Ohm's law again. We can say that I is V over R, which is 20.5 divided by 12 kiloohms, which is 1.7083 reoccurring milliamps. So that's the current that we need in this current source, or flowing out of that current source rather, to yield the diode on the edge of conduction. So we'll do F. And F is a voltage source of unknown voltage with the diode in series and with a resistor to ground, and then a current source in parallel with the resistor. And the current we know is 0.6 amps. What voltage do we need to put on the, or to have across the voltage source in order to yield the diode on the edge of conduction? So, oh, I haven't put the resistor value on, have I? 12 ohms. So this is 12 ohms. So we can put on our diagram our usual, the diode is on the edge of conduction, so 0.7 volts across there, anode greater than cathode, and of course there can be no current flowing in the diode. Oh, I didn't put the direction for the current source either, did I? It's up the page. There we go. Alright, so, well, we can work out what the voltage on this node here is. That's the first thing we've got to do, because we need to know what voltage the cathode is at. Because we know that once we've got the cathode voltage, we'll add 0.7 volts to it, and that will give us the anode voltage, and the anode voltage with respect to ground is equal to V, and V is what we need to find. So we need to apply Ohm's law to the 12 ohm resistor in order to find the voltage that's across it. So we'll do V is I times R, which is 0.6 amps times 12 ohms, and that will be 0.6 times 12, put it down in your head really, 7.2 volts. So we ought to have 7.2 volts there. Now, I know the arrow is that way because I know that the current that's leaving this source is flowing out of there, along there, down there, through there, along there, and up there. So for this resistor, the voltage source and the current that's flowing, for this resistor, the voltage that's across it and the current that flows through it are in opposite directions, and that's correct for a resistor because it's dissipating power. So we can say, well, I've got 7.2 there, I've got to add the 0.7, so that means across here, so this node here, I need 7.2 plus 0.7, which is 8.1 volts. 7.2 plus 0.7. And that's the same as my value for V, because I've got my positive side of my source is the same as the arrow direction on my new voltage arrow. So 8.1 ought to be the voltage that gives us the on the edge of conduction condition for the diode. Did I do that wrong? I did do it wrong because I can't add up. That's not very good, is it? 7.9. 7.2 plus 0.7 is 7.9, not 8.1. There we go, first mistake. And what a simple one it was too. So, last one for question 2 is a 5 volt source with a resistor in series with it, which is 2 kilo ohms, and then we've got a diode to ground, and then we've got a resistor in parallel with the diode, and then we've got a current source in parallel with that lot, and the question asks what's the value of I required to put the diode on the point of conduction. Oh, I didn't put the resistor value in, did I? It was 3 kilo ohms. 3? Yep, 3 kilo ohms. So we do the same thing that we always do with these, which is that has to be 0.7 volts, and there can be no current down there. It's got to be 0 amps. So we know that we must have 0.7 volts across this resistor, so we can work out what the current is in the resistor as well. So we'll be looking for this current here, and we'll say that I is V upon R, Ohm's law, and that's 0.7 divided by 3 kilo ohms, and that will be 233.33 microns. And we can say, well, we know that this current must be flowing from somewhere, and we know that there must be some current through here as well. And we can also say, well, we know what this voltage is, because we know that we've got 0.7 volts across here, and we know we've got 5 volts in that direction. So we can say, well, whatever's across the resistor must be 5 minus 0.7, because we're doing the voltages around this loop here adding up. All these things are in parallel, so they count together. So 5 less 0.7 is 4.3 volts, so we can say that the So this is I in the 3K, and we can say that I in the 2K will be 4.3 V upon R, it's 4.3 divided by 2 kilograms, which is 4.3 over 2E3, 2.15. How did I not do that in my head? 2.15 milliamps. So we know that we've got 2.15 milliamps just there, and we know that this one is 233.3 micrograms. Okay, and we know there's no current there. So we can say, well, if I've got some current here coming into this, all this business here is one node. So I've got entering into this node 2.15 milliamps, leaving this node, nothing, leaving the same node, because it's all one thing, 233.3 microamps, and then I've got leaving this node an unknown amount. Well, I can't have any current sort of sitting on the node just wondering what to do with the rest of its day. If the current's coming in, it's got to be leaving somewhere. So I can add up the currents on this node, flowing into and out of this node, and figure out what the mystery current has to be. And I can tell by looking at the direction of the arrows that the current has to be going outwards, down the page, because there's current coming in from here, there's current leaving there. This isn't as big as that, so there's current down there as well. If this was bigger than that, that current would be upwards, but it isn't, so we're in the situation we're in. So I therefore is equal to 2.15 milliamps minus 0 amps, which is from there, minus 233.33 recurring micrograms, which is, that's equal sign, (2.15) E minus 3 minus 233.33 E, no, do the right number, 2 3s, minus 6 is 1.91 6, and then we can't say because we didn't use enough 3s, but the calculator says 7, so this is milliamps, and that should be the current that has to go down there, and that's equal to our current I.